Hello. Welcome to my channel. In the previous video we have introduced the ellipse and its elements like the major axis and the minor axis that meet at the center of the ellipse. Furthermore, there are the points of intersection between the ellipse and the axes that are called vertices, and the foci. The foci are 2 points that lie on the major axis, are symmetric with respect to the center of the ellipse, and every point of the ellipse satisfies the equation p times f1 plus p times f2 equals k, where k is equal to the length of the major axis, if we call A the major semiaxis, and B the minor semiaxis. The ellipse in figure have constant k equals 2a. The abscissae of the two foci are minus square root of a squared minus b squared, and square root of a squared minus b squared. Eventually we have calculated the equation of the ellipse, with axes parallel to the Cartesian axis and center at the origin. That is x squared over a squared plus y squared over b squared equals 1. Let's see how the things change when the ellipse has the major axis parallel to the y-axis. We rotate the ellipse 90 degrees to get this result. We still call A the semiaxis parallel to the x-axis. That now is the minor semiaxis. And B the semiaxis parallel to the y-axis. That is the major semiaxis. The foci lie on the major axis, so this time they have coordinates 0, -c, and 0c. We know that for each point of the ellipse holds p times f1 plus p times f2 equals k. When the ellipse has major axis parallel to the x-axis, we have k equals 2 times a. Let's see if the things change now. We write the framed equation with v2 instead of p. The vertex v2 has coordinates 0, b. So we get b minus c plus b minus c. That is equal to 2 times b. This means that the constant k is always equal to the length of the major axis. Let's calculate now the value of c. In the previous case it was equal to square root of a squared minus b squared. But it's impossible now, because b squared is bigger than a squared. We know that v1 times f1 plus v1 times f2 equals 2b. Using the coordinates of the 3 points, we get that b equals square root of a squared plus c squared. Therefore c equals square root of b squared minus a squared. We are not going to derive the equation of this kind of ellipse, but if you want to do on your own, you'll find that it is the same equation we had found in the first part. So the coefficient of x squared is 1 over a squared, with A equal to the length of the semiaxis parallel to the x-axis. And the coefficient of y squared is 1 over b squared, with b equal to the length of the semiaxis parallel to the y-axis. And this is true for every ellipse with axes parallel to the Cartesian axes, regardless of which axis is greater. We want to see what is the equation of an ellipse with center at a generic point. Let's draw an ellipse of center C of coordinates xc and yc. Then we consider another coordinate system x' and y', with the origin at the point C. In this new coordinate system, the center of the ellipse coincide with the origin, so its equation is x' squared over a squared plus y' squared over b squared equals 1. If we find the relationship between coordinates of the two frames, we'll find the equation of the ellipse of center xc and yc. Let's consider a generic point P. It can be described by the coordinates x and y in the first coordinate system, and by the coordinates x' and y' in the second coordinate system. We can see that x equals x' plus xc. So x' equals x minus xc. And we notice that the same thing is valid for y and y'. Therefore y equals y prime plus yc and y prime equals y minus yc. At this point we can write easily the equation of the ellipse in the coordinate system x and y. And we get x minus xc squared over a squared plus y minus yc squared over b squared equals 1. Therefore this is the equation of an ellipse with axes parallel to the Cartesian axes and center at a generic point of coordinates xc and yc. Eventually we introduce a quantity called eccentricity of the ellipse that measure how much the ellipse is flattened. It is defined as the ratio between the focal semiaxis, that is half distance between the two foci, and the semi-major axis. The half distance between the two foci is actually the distance of the foci from the center of the ellipse, being the foci symmetric with respect to the center. In the specific case of the ellipse in figure, the center of the ellipse coincide with the origin, so the focal semiaxis coincide with the absolute value of the abscissa of the focus. This is equal to square root of a squared minus b squared. Therefore the eccentricity is equal to square root of 1 minus b squared over a squared, where b is the minor semiaxis, and a the major semiaxis. In our case a equals 6 and b equals 4. So the eccentricity of our ellipse is square root of 5 over 3. That is about 0.745. The eccentricity is a number greater than or equal to 0. And lesser than 1. When it is equal to 0, there is only one focus that coincide with the center. And this means that the ellipse is a circle. On the screen, you can see how an ellipse of semi-major axis equals 6 changes, varying the value of the eccentricity. The bigger is E, the more flattened the ellipse is. And since we are keeping fixed the value of A, increasing the eccentricity means that the value of b decreases. The value 1 is not acceptable, because the ellipse would become a segment, with the foci as its ends. Well, this video is over. If you like my videos, you can subscribe to the channel. See you soon with another video. Bye.